two.
Oh,
Yeah, and one experiment.
It's confusing.
Right.
Are they just, is there just that it's confusing or is there having
Yeah, basically.
So we'll do it right.
Yesterday, the first one
I'll start at 2 o'clock.
Yeah, you should.
Yeah.
In the limit there.
I see. Are we supposed to be on space? Because the group saying
We should go ahead and get started. Alright, welcome back everyone. First seminar of the semester. Very happy to have Sarunas Verner from University of Florida here. Sarunas got his PhD under Keith Olive at University of Minnesota. He's now a postdoc at Florida and is going to tell us about astrometry and ultralight dark matter. Thank you.
Dave. So I'm very happy to be at NYU and I'm extremely excited to give this talk. So once again, thank you for the invitation. And I'll talk about the astrometric detection of ultralight dark matter. And it's a project that I did recently with Jeff Dror, who just joined University of Florida last year. And if you're interested in the details of the paper, please check out the archive link below. So moving on, I'll start with the outline, what I'll be discussing today. So firstly, I'll just discuss the general properties of ultralight dark matter. I'll be considering ultralight dark matter with typical mass scales below 10 to the minus 22 eV. So with astrometry, we will I'll show how to probe masses that are actually below the 10 to the minus 22 eV range, which means that it can only be a subcomponent of dark matter, but I'll still show you the methodology. So after reviewing the properties of ultralight dark matter, I'll move on to astrometry and just how to use astrometric deflection of dark matter to probe for ultralight dark matter. After that, I'll just discuss briefly the discussion prospects and how we can use very long baseline interferometry and optical service to potentially detect ultralight dark matter. And I'll show very nice constraint plots and how the dark matter energy density scales as a function of mass and what sort of masses we could actually probe with this method. And finally, I'll just briefly mention the future directions and projects that I'm working on right now, and we're finishing a couple of papers related to astrometry and also pulsar timing arrays. So moving on, I'm just very briefly going to summarize some key properties of ultralight scalar dark matter. So we know that quantum pressure from the Heisenberg uncertainty principle will prevent the ultralight particles from forming small-scale structures. And to understand it better, we can just put it in the perspective if we start considering the Broglie wavelength, which we know that it scales inversely as 1 over the divided by the momentum, which is equal to 1 over mass times the velocity. And if we put in some numbers relevant for the ultralight scalar dark matter, we get something of this form, meaning that if I'm considering the mass of approximately 10 to the 23 eV, and I take a typical velocity in the galaxy to be 10 to the minus 3, I can expect the Broglie wavelength to be of approximately 600 parsecs. And the key point here is that, of course, as the mass decreases from this general expression, again, very simple, the Broglie wavelength expression, we can see that the Broglie wavelength will keep increasing. So we will probe masses from 10 to the minus 22, 23 down to 10 to the minus 33 eV. So now, again, just to understand some properties of ultralight scalar dark matter, again, I'm just giving a very basic view of that. The number density, because it's non-relativistic, is given by the energy density of dark matter divided by the mass. But now we want to understand this number, how occupation number of dark matter changes because we are considering wave-like dark matter. So that, of course, if we take some parameter delta n, and divide by the delta x cubed, the volume element at the delta p cubed, we can find that the number density of dark matter over k cubed leads to a very, very large occupation number. So if I'm using the dark matter energy density with the local dark matter energy density of 0.3 GeV per centimeter cubed, and also setting the ultralight dark matter mass to be 10 to the minus 23 eV, I can expect a huge occupation number. So again, this number is really, really big, 10 to the 96, meaning that we can consider, obviously this is wave-like dark matter, and we can consider classical field theory to describe the key properties of ultralight scalar dark matter. So now to put it in the perspective, like how big this number is, and I'll keep calling this particle axion, even though this is not the QCD axion. Of course, this is an axion-like particle, but I'll commit a sin of I'll just keep calling it axion. This is just, so if I'll, when I'll say axion, I just mean ultralight scalar dark matter here. So to put it in the perspective, we know that we have 10 to the 18 grains of sand on Earth, and to fully match this number, we would need to count grains of sand on 10 to the 78 Earth. So again, this number is huge, and these occupation numbers for ultralight dark matter get really, really high. Another perspective would be that we know that there are 10 to the 80 atoms in the observable universe, and that would correspond to the atoms in 10 to the 16 observable universes. So again, this number is really, really big. Now, of course, another question is how light can this dark matter be? And we will be considering masses down to 10 to the minus 33 eV, because below that mass, it starts behaving like dark energy, and you still have a slowly rolling field. And I'll very briefly discuss what happens below that mass, because we believe that we're still working on it, but we will try to understand how we could actually use astrometry to probe models of quintessence and early dark energy. And that would require to see what happens below this mass range, but again, this is work in progress.
I hate to ask such a
Yeah.
stupid question, but in what sense does it need to be scalar? What is scalar about it?
Scalar, so
Is it just because you need it to be a
so
boson?
it doesn't have a spin. Yeah, so this is just like a classical.
You need it to be a boson because you have high occupation number.
Exactly. So I have classical.
So
scalar
really it's
field theory.
bosonic.
It
Yeah,
probably
yeah.
doesn't mean it can't be pseudoscalar.
Yeah, no, I don't mean that. Yeah.
Right.
But actually, something that we're working on is we're working on ultralight vector dark matter, and it has very, very different properties. And using astrometry, I'll just briefly mention it, that you can distinguish between scalar and vector because of the directional dependence. So that's something that we haven't published yet, but also pulsar timing array signals will be very different, and astrometry would also give very different signals for vectors, and that's something that we haven't finished yet, but like it should come out very soon. So I'll talk about it a little bit later, but but for now, I'm just considering simple scalar.
So just out of curiosity, how does this number compare to the entropy in, say, black holes? I mean, that looks like it might be the dominant component of entropy in the universe.
That's a good question. So I haven't thought about it, but this number is simply coming. So if I have the simple, if I have a scalar field, and if I have a again, I have some Hubble friction terms, so when mass becomes lighter than this one, it means that it behaves as dark energy because it basically freezes. So I only thought about it from this perspective. I haven't thought about the entropy. Yeah, so I don't know.
How do you keep this mass so small? Why is it natural?
Natural. I don't know. The number, you mean 10 to the minus 22 or the?
10 to the minus 22.
I guess you could still have like an axion light particle, which could give you like something, it wouldn't be a QCD axion, but at least 10 to the minus 22, you could still have some mass coming from lambda over, like from non-perturbative effects, like lambda over f squared, and if lambda is small, exponentially suppressed coming from the non-perturbative effects, and fa squared is your typical axion decay concept, which could be very large, that could lead to masses of 10 to the minus 22. So again, non-perturbative effects, but not, again, this is not a QCD axion, so it doesn't solve the strong CD problem.
But you will need also some gauge fields to give a lambda, right? Because you say lambda over f. So aren't they also part of the matter?
Well, that I'm not exactly sure, because I think you can still have something like a pseudo-scalar, and sure, like the scale of lambda, this is a little bit maybe fine-tuned in a way, but I think you could still like If you're not considering the exact use of the axiom, I still think that you don't probably need a gauge for that. You could have a simple scalar and just non-perturbative effects, something like axiom-like potential, something with a cosine leads to non-perturbative effects. So probably low masses, like it's more difficult, like theoretically it's maybe more difficult to get to such low masses, but yeah, I'm not sure. I'm just, for now I'm considering just agnostic approach. I have some very light scalar dark matter which has classical properties, and it's basically oscillating, and it can be described by classical field theory.
It's a big occupation number.
Yeah, very, very big.
Background where, say, the expectation value of this
Yeah.
scalar is non-zero. Wouldn't that give you spontaneous symmetry breaking for parity? Because I mean, now you have a very big classical field.
I think that that's actually model dependent, but for now that we're considering, we're just adding a scalar, which is, again, I'll show you in the next slide what the field. And for here, like, we just try to do it like just agnostically without actually thinking about the fundamentals of this field. So just fuzzy dark matter. So this is what
But I mean, we know that there are some, so the
yeah.
universal contributions to the mass, etc., are compatible with such a mass. So
Yes,
say
yes, they are.
gravitational interactions do
Yes.
not create.
Yeah, it's compatible.
big mass.
The only real constraint for full dark matter, well, there are a couple more constraints, but you have like Lyman alpha constraints and density, contrast, and structure formation constraints coming from cosmology. But in a way, if you just introduce the scalar field, you can like, no one's really stopping you from doing that. So there are some astrophysical constraints. But to get around these constraints, when you're moving below the Lyman alpha constraints coming from the linear matter spectrum, the caveat here that it can only be subcomponent dark matter when you move below 10 to the minus 22. Okay. So moving on, I just wanted to show that again, if we move to this extremely light mass range, then it leads to extremely large number. And again, this is the range that we're considering from 10 to the minus 33 to roughly 10 to the minus 22. So yeah, subcomponent dark matter. So here's just the simple idea of classical oscillating scalar field. So this is the general form that for wave-like dark matter that can be used for your classical scalar field. And here, A is the amplitude, omega is the frequency, and alpha is some slowly varying phase that we have. So this slowly varying phase is going to have some components that depends. This is the field velocity relative to the cosmic frame. So this is how we are getting the slowly varying phase. And alpha is some randomly sampled phase that is sampled every coherence time and length. So this is how we're expanding our classical scalar field.
Quick question?
Yeah.
What's like a humane range for V? Like, can it go all the way up to speed of light? Can it start at 10? Or like, what should I expect the velocity to be at random?
I think it's roughly of 10 to the between 10 to the minus 4 and 10 to the minus 3, 10 to the minus 4, 10 to the minus 3. That's the typical range. And that actually just comes from I think that's the range.
I'm not understanding what you mean by they're randomly sampled.
So it means that every coherence length I can expect, because of wave-like properties, I can expect to have different coherence time, different phase. Because this alpha is not, I don't know the actual value of my alpha. So when I have a big sample of
Well,
particles.
that could be a definition of coherence time and coherence.
Yeah, that's right. That could also be the definition. Yes, that's another way to look at it. And the field momentum is defined by we're just taking the gradient of the slowly varying phase, which is again just k is equal to the gradient of this alpha. So moving on, of course, because it's a scalar field, it has to satisfy the Klein-Gordon equation. which leads to the usual frequency that omega squared is equal to k squared plus m squared. And in the non-relativistic limit, it leads to omega equals to m plus k squared over 2m. But if we only care about the leading order correction, we can approximate that omega is just equal to the mass. And the gradient, the k squared pieces are usually negligible. So because it's a gradient. For now, in the derivation, I'm keeping the k squared contribution, but I'll show you that you can simplify it, and then it just leads to, again, a simple approximation that omega is equal to m. So moving on to the energy momentum tensor of a scalar field. So if I'm taking a flat background, which is just given by this energy momentum tensor, I can simply carry out the computation of the components of my energy momentum tensor. And for this particular scalar field, using the expansion that I showed in the previous slide, I compute the zeroth component is going to give me the energy density. So again, this is just rho is equal to T0, 0, and I compute the energy density this way. And I also find that the diagonal pieces TII will give me the pressure contribution. And the off-diagonal pieces, or TIJ contributions, are going to lead to the momentum density. And the off-diagonal, the remaining pieces, the TIJ minus the P delta IJ contributions, are going to lead to anisotropic stress. And I'll be interested in computing the scalar potentials, Newtonian potentials phi and psi. But to do that, I only need two Einstein equations. So I'll use the combination of any of these two to compute the known variables, which are my Einstein potentials, and I'll show you that in the next slide. Here I just use my line element to compute the scalar perturbations caused by this oscillating ultralight dark matter. And now I'm only interested in scalar perturbations. Of course, they are vector and tensor perturbations, but we found them to be subdominant, so the leading effect will come from the scalar perturbations. But that's only true for scalar dark matter. If we actually move on to vector ultralight dark matter or tensor ultralight dark matter, this picture changes and you get very, very different limits. And that's something that we're working on right now. But again, for now, I'm just focusing on the simplest possibility of scalar dark matter. So phi and psi is just your scalar metric perturbation and then Newtonian gauge. And we did the computation in general. Well, we also computed in gauge invariant, in terms of gauge invariant Bardian variables. And we also used the synchronous gauge to get the same result. But again, for simplicity, I'm just showing I'm just going to be using the Newtonian gauge. So now, when I do that, I move on to the linearized Einstein equations. And in the weak field limit, I can use the Einstein equation to set my left-hand side of g mu nu to the right-hand side of the energy momentum tensor to find my Newtonian potentials phi and psi. So if I do that, I find like the energy density from the Poisson equation. I also find the pressure from this Einstein equation. And if I wanted to do this computation differently, I could also use that momentum density or anisotropic stress expression. So because we only have two unknowns, which are the scalar metric perturbations psi and phi, we can use any combination of these two. We can combine any two expressions to compute the Newtonian potentials or gravitational scalar perturbations phi and psi. So I just wanted to show a very simple simulation of what happens when you sample it. I fixed the mass to be 1, the velocity to be 0.25, and then I fixed the coherence time to be equal to 10, and then I sample alpha and k hat every coherence time, which I just set to be equal to 10 in the arbitrary units. And you can see that I get these sharp corners, and that the behavior of my oscillating field changes every, t equals to 10 in inverse mass units.
Sorry, what's the y-axis and how are these units?
Oh, these are just arbitrary units. So I'm setting mass equal to 1, and then from that I can figure out the remaining units.
Well, what's the y-axis supposed to be?
The y-axis is the a over a naught, so this is the amplitude. Yeah, how amplitude oscillates. So, but the reason why I wanted to show that is because and I wanted to show how the teeny new elements, the elements of the stress energy tensor would change. And again, every coherence length you have slightly different behavior because of the sampling. And here I just wanted to show that the average energy density, of course, is equal here to 1/2, but it's still oscillating, so that will lead to observable effects, because the key point here is that the average pressure is 0, but it's still oscillating, and these oscillating effects will lead to some observable effects that you could detect with pulsar timing arrays and astrometry. And for completion, I also include the momentum density piece, that basically the average momentum density is equal to some constant displaced from 0, and similarly, anisotropic stress gives you also some constant value. And here I'm just showing the value of Qx, energy density, pressure, momentum density in the x direction, and anisotropic stress also in the xx component. So again, the key point here is that even though if I'm just focusing on the energy density and the pressure, the average energy density, of course, is just 1/2 m² a², and the pressure is 0, but because that will, if I'm not considering the average and just taking the actual oscillation, it will lead to observable effects. Okay, so this is just now the summary that again, I'm using the energy density and the pressure to compute my gravitational potentials. And here I impose a simple ansatz where I'm decomposing my gravitational potential, and I'm taking the Newtonian potentials phi and psi to be of the following form. So I'm assuming that there's some time-independent contribution, which is not observable. Then I decompose it in terms of the sine and cosine functions. And if I plug it into the Newtonian linearized Einstein equations, I can compute that I can find that my phi, psi, and psi contributions are 0. But then the key point here is that I can compute that my Newtonian gravitational potential psi is actually not 0. So this will lead to observable effects in pulsar timing arrays and astrometry. So exactly this potential. So now, if we put in some numbers, for the local dark matter energy density of 0.3 GeV per centimeter cubed and the mass of 10 to the minus 23 eV, we can expect the absolute value of this gravitational potential to be approximately 5 times 10 to the minus 16. And again, I'll show you why it's observable and how to differentiate it from the background. So now moving on to astrometry. So again, I just introduced some very, very simple features of oscillating ultralight dark matter, but now I want to show how to combine it with astrometry and how to observe, how to potentially look for such light dark matter candidates. So I'm just going to give a very, very brief overview, starting with parallax. So astrometry focuses on accurately measuring the position and motion of stars and other celestial bodies. In particular, in our sample, we'll focus on quasars, and we'll use the astrometric detections of quasars, and again, we'll mostly focus imposing our limits from VLBI and some optical observations such as optical missions such as Gaia. And there are some future missions that will also could be used to improve these constraints. But getting back to astrometry, so here's just a simple picture of parallax and how the parallax measurement works. If you have some distant stars that are not moving with respect, that are just behaving as a fixed background, and in January you look at the star from point A here, and then 6 months later, using Earth's annual motion around the sun, you do the same measurement, you can see that the star moves, and of course you can then compute the distance to the star in parsecs, and theta is your parallax angle in terms of arc seconds. So this is just a very, very simple picture of how ancient, just simple parallax measurements work. But of course, we'll be considering something more complicated, but we'll generalize to large samples of data and apply for, use VLBI data and Gaia data and again, other optical circuits. So So I just wanted to briefly show a little bit about to discuss the history of astrometry and how it improved significantly and why it's now important to look at how astrometry could help us to detect dark matter and maybe even something different. But if I'll just very briefly, I just very briefly want to show how our astrometric measurements improved throughout the years. So here are the key moments in astrometry, in the history of astrometry. So if we start with 200 BC, Hipparchus compiled his first catalog, which contained approximately 1,000 stars, and he achieved a precision of less than 1 degree, and he only used the naked eye observations. So again, this was a relatively big achievement given that it was done in 200 BC. So now, moving on to the late 16th century, astronomer Tycho Brahe actually measured the positions of also approximately 1,000 stars, but now he used quadrants and sextants to improve his measurements, and he managed to measure it to the precision of about 1 arc minute. So again, this is a big improvement. If we look at this picture, we see how we went from measurements done by Hipparchus to the measurements done by Tycho Brahe. So again, this is a significant improvement in terms of the angular precision. But these were like naked eye observations, and now we move on to 1725, when English astronomer John Flamsteed finally published his first stellar catalog using a telescope, which contained 4,000 sources, and it was done with a precision from 10 to 20 arc seconds. So again, this is, if you look at this plot from Hipparchus to Tycho Brahe, and then Flamsteed, this is a very, very big improvement. But now, when we enter the era of space missions, it becomes the astrometry improved significantly, and Hipparchus space mission back in 1997 released their first catalog, which contained the position and parallaxes and proper motion of approximately 120,000 stars. And the precision was already reached 1 milliarc second. So again, this is you can clearly see from this plot how it actually improved. So this is a very impressive achievement. And now the Gaia mission, which was launched in 2013, will chart a total of 1 billion stars and will measure the position and parallaxes with precision down to 10 microarc seconds. So again, this is a very, very big improvement. And I believe that the last data release of like DR5 of Gaia is supposed to come out in 2030. And again, we can use this data and apply it for astrometry and dark matter measurements. So this is just a final general generalization that I found on ESA website, just astrometry through the ages, and I really like this plot. So I just wanted to show like, again, how we started with Hipparchus in 22nd century BC, and then we moved to Tycho Brahe, John Flamsteed, and then of course we have lots of these optical measurements, and then using telescopes, and then we move on to Hipparchus space mission, which you can see from the background that the precision, angular precision keeps improving, and we keep measuring larger samples of objects. And finally, Gaia mission, which was launched in 2013, and which contains a very, very big sample of stars, and we're expected to move to, it's expected to measure a total of like approximately 1 billion stars. Okay, so moving on to high precision astrometry, I'll just briefly discuss how we got the idea to apply to dark matter, and how we can use high precision astrometry and these astrometric measurements to probe for dark matter. So it was shown by Book and Flanagan in 2012 that the high precision astrometry can be used to detect gravitational waves. And then, of course, if you have a single source, and you can expect that your angular velocity is just equal to angular accuracy divided by the observation time. However, as the sample keeps improving and you get to the n number of sources, that show you can expect that the correlated angular velocity should be detectable by, you get a 1 over square root of n improvement. So it means that higher the number of sources you have, the better prospects are for, the better sensitivity plots, the better prospects for detectability you can expect. And also here, of course, like we can, I'll discuss it a little bit later, but I'm just briefly mentioning that VLBI measurement and radio astrometry usually has a lot better precision, but has a smaller number of samples, whereas the optical is the other way around, where we don't have such a good angular resolution, but we have a significantly larger number of sources. So there's a trade-off, and you'll see that in my sensitivity plots. So moving on, the idea by Book and Flanagan, which we used as the inspiration for our work, was that the stochastic gravitational background will cause apparent angular deflections which are correlated over the sky, and they vary randomly with time. So again, because we have a large number of quasars, and we have some stochastic gravitational background, we should be able to see these fluctuations when we take a very large sample of sources. So, if we have some root mean square deflection given by this expression, we know that it's proportional to the strain amplitude, and the strain amplitude is equal to the h naught divided by the frequency times the square root of the gravitational wave energy density. So again, this is just the general idea that they had in their paper that we wanted to extend using their formalism for ultralight dark matter. And then of course you can do some algebra and figure out the upper limit on the gravitational wave energy density and the sensitivity levels that you can expect to detect. So the upper limit for this gravitational wave energy density is equal to the angular precision square divided by the number of sources times the observation time squared times the Hubble parameter squared. And if to put it in the perspective, if we take the Gaia measurement of n 10 to the 6th, well, let's say I'm taking 10 to the 6th samples, even though like Gaia is expected to measure more samples, but for now I'm just taking 10 to the 6th. The angular precision is given by 10 to the 10 micro arc seconds, and the observation time is equal to 10 years. We can expect the sensitivity levels to be less than 10 to the minus 6. So again, this is a very good sensitivity, and you should be able, using these sensitivity levels, to differentiate from the stochastic gravitational wave background.
So one question.
Yeah.
What's the correlation length over the sky? Like how do you? It depends on how this gravitational background was produced, I guess, right? Because in general, it may not be correlated over the sky.
Yes, that's right. So we know that the strain is supposed to be roughly 10 to the minus 15. Let's see. Minus 15. Yeah, I'm not sure. I don't exactly remember the number.
I think, yeah, I read this book in Flanagan paper. So it's mostly the what they call the Earth term. So the phase of the gravitational wave and the direction would be random, but the period is so long that it has some direction and some polarization amplitude, and that will define a quadrupole on the sky. So these angular deflections will be mostly quadrupolar in nature with very small octopole and higher multiple numbers.
I see.
But yeah, the pattern is random, but it's mostly quadrupole, and it's set by the phase of the gravitational wave.
Yeah, thank you. Okay, so using the derivation provided by Book and Flanagan, we thought about how can we use it to detect gravitation, how to gravitationally detect dark matter. So this is a simple example, like in the absence of metric perturbation, when there is no dark matter, we have some light emitted from the source, and then it's moving towards observer, and here I'm defining the vector n hat that is pointing from the observer towards the source, and the photon is traveling from the source in this direction, and I'm introducing the 3 momentum vector here. But now we know that from this geometric description, light travels in the minus n hat direction with frequency omega naught. And this is just choice. This is how we define our system, and you can do it differently. But the observables that are physical will not depend on the choice of your just basically your coordinate system. So lambda, we choose the affine parameter of the observer to be, we set it to be 0, and this is the affine parameter of the observer. So when you see the quantities that will have some that are evaluated at 0, that means that they are evaluated at the observer's point, And then the distance to the source is given by this expression lambda s is equal to minus the absolute value of the distance divided by the frequency of the photon.
Sorry, what's lambda s? What's lambda s?
Affine parameter of the
Oh,
source. source. Yeah. So it's just minus xs divided by the frequency of the emitted photon. And if I'm just taking this expression here, so with this setup, I can compute my forward position and for momentum. And again, I'm just giving these expressions using the setup, the geometric setup that I showed here. But now, that was the setup when there was no dark matter. But in the presence of dark matter, you get these oscillations that will change this whole picture. And you're going to have some perturbations for the photon and the source and the observer, and the n hat is also going to have some perturbation. So this is the key point that I'll use for astrometry, is I know that the deflection, angular deflection is going to change because of this perturbation, and that's what we're computing. So I'm using the same expression as before for the forward position and for momentum, but now I'm adding this perturbation, delta x mu and delta p mu for the momentum. So again, I'm using the first order perturbation theory, and I'm only working with the first order correction. So now, another point that I wanted to mention is that dark matter leads to a total of 3 gauge dependent effects. And of course, the physical quantities are supposed to be gauge independent, so we checked the computation using the Newtonian gauge, the synchronous gauge, and then we finally did the derivation using the gauge invariant Barting variables. And then the gauge dependent quantities are the following. So the photon path is perturbed, so that we know that delta x mu and delta p mu are going to change. Then we know that the source and the observer ward line is also perturbed because of the presence of the oscillating ultralight field and the gravitational fluctuations. We expect that the source will wiggle and the observer will wiggle as well. And then finally, because we need to compute everything in the observer's frame, we know that the frame would also be deformed, and there's going to be a perturbation in the observer reference frame as well. So we're introducing the perturbation. We'll need to compute the perturbation of the local proper reference frame. So moving on to the physical and quantities in the observer frame. So here the hatted frame will correspond to the observer frame, and the unhatted frame will will correspond to the coordinate frame. And we define the local proper reference frame to be the equal to E mu non-hat component to be equal to the observer's forward velocity. And finally, we're using these tetrads to satisfy this trivial condition that eta mu nu, when you multiply by 2 tetrads, you're going to recover the same flat Minkowski metric with in the hatted frame. So now if I'm computing, so I need to compute the forward momentum of the source in the observer frame, and that corresponds to the hatted frame as I mentioned here. And I need to, I'm looking for P alpha hat contribution, and then I find that the energy, P0 component, P0 hat component is given by this expression, and then PA hat is given, the free momentum is given by this expression. And again, this will account for all the contributions that we have from dark matter. But now the key point that we care about is that to find the deflection of the source, we'll need to compute the forward momentum in the observer frame, which is coming from the perturbation of the forward momentum here, the delta P alpha piece. And the apparent direction of the source will change because to compute the apparent direction, the delta ni hat contribution, we need to compute this expression coming from the forward momentum. So again, this part gets a little bit technical, so I'll be just showing a couple of slides now, but I'll just show the key ingredients that we're using to compute the bearing direction of the source. But to compute this quantity, we essentially need to compute the quantity delta p mu at the observer and also the perturbation of the local proper reference frame at the observer. So again, I'm just briefly mentioning that I mentioned before that we did the computation in different gauges to show that it's, well, we wanted to be, we were cautious, we wanted to make sure that we get the same result in different gauges, and eventually we did the full computation and included it in terms of gauge invariant bargain variables. And of course, it's a very difficult computation, but we did it in terms of Newtonian gauge, synchronous gauge, and then using the bargain variables. So this is just, I'm going to just show a little bit of math, but these are just the key steps that we had to do. So now we need to compute these perturbations, we simply need to use the geodesic equation. And it gets, there are ways to simplify these expressions because the time and space component in the different equations are analogous when you're using the limit that psi gravitational potential is equal to -phi that I showed from the computation for ultralight scalar dark matter. And this leads to this very nice symmetric form, and that significantly simplifies the computation. So you can do that like Book and Flanagan, they provided a full general computation how to do it in the synchronous gauge, but because we're using we exploited the properties of oscillating ultralight scalar dark matter, where we get the symmetry because the anisotropic stress is maximized because psi is equal to -phi. So that leads to very, very nice and symmetric forms in form momentum. And then if we use these expressions, we can also compute the position delta x lambda. So again, we're just using the same geodesic equation, integrating it again, and get this expression. So we also need to do the same thing for the source and observer location using, again, the same geodesic equation, but now instead we're plugging in not the forward momentum, but the perturbation of the forward position of the source and the observer, and again, just scaling out the algebra. And then we just do the integral and find the following results. So the key point here is that the lower bound of the integral is taken to be at some physical reference point because when we're integrating it, we have some lower bound, but this lower bound is just going to give us a constant which is not measurable. It's not time dependent and it's not observable. So therefore we have dropped it because it's done in a measurable integration constant. And finally, we integrate it once more and just get the remaining ingredients for delta x observer and delta x source. This is just, again, the last conceptual part that I wanted to show with the computation, that for it to physically make sense, we need to impose the correct boundary conditions, and we're imposing the following boundary conditions, which there are 4 boundary conditions that can be understood physically. So the first condition is that always has to be satisfied is that the photon geodesic is null. So we know that eta mu p nu is equal to 0. This is just our usual expression from GR. And even though we have these perturbations, this photon null geodesic expression still has to be satisfied. So that gives us one boundary condition. The second boundary condition is that we know that the photon frequency is emitted at the frequency of omega naught that I showed before. This is just our photon frequency. So we use this property to also find some delta p naught contribution from that I showed from the geodesic equation. And then the 2 remaining boundary conditions is that we know that the emitted photon and the observer, because the photon has to reach the observer, meaning that the photon and observer word lines have to intersect. So, and that leads to another boundary condition that we can use to get the result. And finally, the analogous condition to that is the photon and the source word line would also need to intersect, meaning that just as we need to observe the photon would also need to be emitted at the source, and this is our boundary condition. So using these 4 boundary conditions, we can carry out the computation and figure out all the expressions that we found from the integrated geodesic equations. So this is just a very brief summary that we have 4 boundary conditions, and we need to compute the observed photon for momentum, and we also need to compute the deformation of the observer reference frame, and these 4 boundary conditions will lead to the apparent deflection that we're trying to compute. So now we have all the ingredients to compute the observed photon for momentum, and with this full setup, we can compute the apparent deflection and finally start considering astrometry. So now this is again just the general picture, just a general summary of the properties of ultralight dark matter and how the oscillating dark matter, which because of these coherent oscillations leads to time-dependent perturbations, and these time-dependent perturbations could be observed using astrometry. So the first method that was used for gravitational detection of ultralight dark matter is based on the gravitational redshift, and that was proposed by Rubakov more than 10 years ago. And they simply compute the effect of time-dependent perturbations on the gravitational redshift, and you can see that if you compute the redshift z, you can see how the frequency, how the observed frequency of the photon changes, and that depends on the gravitational potentials phi at the source and the observer, and you have some higher order corrections, something similar to the integrated Sachs-Wolf effect. So they're usually subdominant, but the main contribution to the effect is coming from these 2 gravitational potentials. So again, this was proposed by Rubakov more than 10 years ago, and he showed the method how it can be used, how can it be measured from the pulsar timing array data. So you can compute the timing residuals and see how the effects of the coherent oscillations of ultralight dark matter would affect the gravitational redshift. So, and our method is that we're computing the astrometric deflection, and then we get a little bit more complicated expression, of course, but after we carry out the computation, we get something like this expression that we'll use, well, I'll show you how I'm using this expression in the next slide, but then it can be measured from VLBI, Gaia, next generation VLA, and hopefully, if it gets approved, the Thea data. So how to measure ultralight dark matter? So there are some kinematic corrections that we need to include to make sure that we can differentiate it from the background. And that includes some kinematic corrections that, again, to make sure that our signal, we need to find a way to differentiate our signal from the background. So there are 3 important effects that we're considering here, the kinematic corrections that we need to make sure are taken into account. So the first one is classical aberration, which is caused by the motion of the Earth around the Sun, or bare center of the solar system. So we need to take into account this effect when looking at our astrometry constraints. The second one is the intrinsic proper motion, which is in a way a negligible effect, because for astrometry we'll mainly be interested in the quasars or extragalactic sources, meaning that this excess suppression is going to be very, very large, and the second term will become practically negligible. So we will not be considering intrinsic proper motion kinematic correction. And then finally, there's a secular aberration drift caused by the motion of the solar system towards the very center of our galaxy, and we also need to take into account this kinematic correction. So just to understand the sizes of these effects, the classical aberration is sizable for every source, and it typically induces proper motion of approximately 100 arcseconds per year for observers that are orbiting the Sun. So again, this is just a ballpark of this classical effect. The second effect that I mentioned is the intrinsic proper motion. Again, I'm emphasizing that for extragalactic sources, the intrinsic proper motion becomes negligible. And finally, the secular aberration effect has been recently measured by Titov et al. And I think they used VLBI data and found this dipole pattern concluding that the secular aberration effects could be range from 4 to 6 microarc seconds per year. So again, we need to take into account these effects when considering astrometric constraints. So to extract the influence, we're taking the near and far limits of our expression, and we get something like this, that the leading order corrections will come from this piece. So we're taking the long expression that I showed before, we're taking this limit, and then we find this expression. So now, from this expression, we need to compare it to the kinematic corrections that I showed before, and this leads to two distinct effects. So the first effect is the annually modulating angular deflection, or the equivalent of the classical aberration effect. So we need to figure out, we need to differentiate it from the background. And the second effect is the secularly varying aberration, which was the equivalent of the secular aberration drift, the third term that I showed in the previous slide. So taking the Earth's velocity around the sun to be 10 to the minus 4, and here the key point is that it's going to be very, very sensitive to low masses. So when we're probing below the 10 to the minus 22 eV range, down to 10 to the minus 33 eV, this term is always going to be dominant because it scales as 1 over m. So it's very, very sensitive to the mass. So the lighter it gets, the better sensitivity we get. So I'm just going to very briefly mention the quasar analysis and just at least the key important points that are relevant for the sensitivity plots is that we're taking a total of n quasars, and we're considering them observed at some time intervals of delta t for a total time of capital T, and there's going to be some instrumental uncertainty sigma theta that we just find from all the missions like VLBI and GAI and so on papers. So we also need to take into account the instrumental uncertainty. So the expected signal, just going to skip over that part, is that we just use the deterministic function for the secular proper motion, and for annual modulation we of course need some cosine contribution. So we're going to have a different, we're defining our theta bar to be different, and then assuming that just using the log likelihood ratio between the signal and the background hypothesis, we can find the following limits for the secular proper motion and the annual modulation. Moving on to the money plot, so these are our constraints that we imposed using astrometry, and as you can see, we're probing down to very, very low masses. So this plot is on the y-axis. I'm showing the energy density of rho GeV in the units of GeV per centimeter cubed, and the local density here is well, here this is a line for 0.3 GeV per centimeter cubed. But because we're considering fractional dark matter and we don't know what sort of energy density for dark matter we can expect, it means that we can actually use astrometry to probe this whole parameter space. So we start with VLBI, that this is our current constraint that's using the available data. So for VLBI, we're taking 50 quasars with the angular precision of 5 microarc seconds.
Sorry.
And yeah.
When you say, I mean, is there, is there a limit for the redshift quasar to you? I mean, in the sense that more than something would affect some parameters or.
Well, for quasars, so typical quasar distances are like from 1 to 10 gigaparsecs. So we're using the range, this range of quasars. But I guess if you would take objects that are further away, you won't be able to use the flat background that I'm using, and you would need to take into account
that's what I'm asking,
yeah. So yes, then there are additional high order corrections that we also computed, but didn't put in the paper. You can use some nice tricks using conformal symmetry and derive these high order effects instead of using flat Minkowski background, you actually use curved spacetime. And for objects that are further away than, I guess, quasar 10 gigaparsec, you would need to take into account all these effects. So, yes.
Why can I not just look at your plot and say that quintessence models are excluded?
Oh, that's what we're working on right now. Yes, that's a good question. Yes, they should have been detected using astrometry. Yes, because when you get really close to this range, that's the quintessence range, and it's not there. So,
But you're assuming everywhere in this plot that the velocity is 10 to minus 3, right?
Yeah,
Which
that's
a
right.
quintessence field need not have in general.
Well, sure, but it depends on what sort of velocities you would assume. So I think that even if you assume some, like, again, like what sort of range we would, like, I think we tried 10 to the minus, from 10 to the minus 3 to 10 to the minus 5, like a relatively broad range, and of course everything changes, but not.
You change this straight?
Yeah. And that would actually, that still probably would exclude quintessence unless there's some clever way to get around these constraints. So that was, you could also probably probe the early dark energy models. So that's again something that we're thinking about, and we're just focusing on quintessence as well, trying to figure out like, unless there's some specific value, like a good justification for a very, very different velocity, not in the range of, I don't know, 10 to the minus 3, 10 to the minus 5, then maybe these constraints would be different. But again, when we made this plot, we played around with velocity, and I think the quintessence part would still be mostly excluded.
I thought for guided theory they did see some like anomalous proper motion for some of the quasars that they couldn't quite explain.
Yes, but again, that part is not like rock solid yet, so we didn't want to like make any assumptions before it's like concluded that they actually see.
Okay, so that's why you haven't filled in the color for guided.
Yeah, that's right, yeah. So we're like, yeah, this is DR3 right now, and then again, I think they're supposed to release DR5 by 2030. So this would improve our constraints, but again, not significantly. Yeah, but I think the most interesting part that we can definitely conclude is like the VLBI data that we have here in this line, and at least the quintessence and early dark energy models should be probable using astrometry. And I guess with VIA data and some future optical missions, we would again get significantly better sensitivity plots.
How is early dark energy constrained by this? Because doesn't early dark energy like decay into other stuff? Isn't the scalar field gone by now? I mean, this is, these are measurements of today.
Yeah, these are measurements of today. So let me think for a second, because I think that early dark, so they typically have introduced scalars that, with their models, aren't there models that become, like early dark energy becomes quintessence later? So I think more like, so initially you can have early dark energy of roughly 10 to the minus 27, 28, and then, well, I guess if it becomes, well, maybe it would be a better thing to say that it constrains the quintessence models. So yeah, because early dark matter, yeah, the energy is that case.
Another question?
Yeah.
So, we know like the current limit on the fuzzy dark matter is around like 10 to the minus 19 V or so?
No, it's 22, right?
There is this paper by Neil Dalal and his collaborator where they improved it. But if even for 10 to the minus 22, should I basically think that you are mostly interested in the like below the cosmic density line?
Yeah, that's right, absolutely, yeah. Because it has to be fractional dark matter, so I can't like, I don't know, like 10 to the minus 19, maybe like for the like Lyman alpha constraints, I think I typically consider like minus 22, 21 eV range to be, but below, anything below that would be considered to be like, it has to be fractional dark matter, but yes, I know the paper you're talking about.
Right, and then for, if it is really at 10 to the minus 24, which is like the limit for your plot, are there expectations regarding how much what fraction is allowed by the current data?
I not yet, because I think to fully understand the dark matter energy density, you would need to run some sort of simulations for very, very low very, very low masses, like even 10 to the minus 24. And we haven't found any papers that would discuss that. So yeah, we looked for papers, but we couldn't find anything. And we were cautious not to, we wanted to do some estimations just using some, usual.
I think there are constraints in that region by René Klozek and David Marsh, and they roughly constrain the density to be sub-percentage.
Okay.
Basically, because if these fields constitute 1% of the dark matter, this field starts oscillating very late.
Okay.
And that can have effects on the CMB power spectrum. So roughly, yeah, in the range you're plotting, I think it can only
So you mean if I would go below the local density, and what was the
It depends slightly. I think, yeah, roughly this range, 10 to minus 24, 10 to minus 3 eV.
Okay.
I think it goes as low as a few percent. So look for papers by René Klozek.
Okay, yeah, I'll look it up. So then I would not, like, this plot would not be extended to such, to local density, and I would have something like smaller.
Well, they're assuming even unclumped dark matter, right? So below the cosmic density.
And do you remember how low what's the lowest mass that they're considering?
Hubble scales. I mean, the bound, of course, does worsen both at the high mass end and the low mass end.
Yeah, I'll look it up. This is something that we've been looking for, but yeah, we didn't want to draw, like, we for now wanted to just make this parameter space because we were not confident with we didn't want to speculate, that's all. Yes?
Can you explain the y-axis again? So it's sensitive to the average density or the local density?
No, local density, so this is just the dark matter
Yeah,
density.
yeah.
And this is the local density that we know from the measurements, which is 0.3 GeV per centimeter cube. And this is just, again, the reference is just the cosmic density, which is like 1.2 times 10 to the minus 6.
Like when you said it's excluded at this range, is that you're saying like?
So I'm just saying that if you have masses that are that low or something where you're reaching the quintessence part, and you use the astrometry and VLBI data, if there was something, we would have seen something in this parameters, because this is, again, sensitivity plots show that this should, if there was something, it should have been detected.
Right, but I meant like how do you translate that into like fraction, let's say, suppose, like dark matter fraction, or?
Oh, dark matter fraction.
Right, because then if you're saying, like, if we're sensitive to the stuff that are like around Earth, then you're looking at the local density as fraction 1, or like?
Well, you see that I think it gets complicated because going to such low masses, because it's because of wave-like properties, your dipole wavelength keeps increasing. So then you're going from local density to some larger and larger structures. So then, like, you can go up to cosmic density, but I don't really know how to constrain for such big dipole wavelengths. So I don't think that we have good, like, actual constraints for that.
So you're saying if you go to lighter mass, then the local concentration will be less than the local density?
Yes, it should be less. Because you're shifting from local towards cosmic and something else. It would, as the dipole wavelength becomes larger and larger, you should expect different dark matter energy density. But this is the whole the point of this plot, that with astrometry you can probe this parameter space.
Students wrap up?
Yeah. Just very briefly. So the future directions that I mentioned before is that now we're working on ultralight vector dark matter, which is giving us very, very different results. And the key point is that because now the vector dark matter is going to oscillate along some direction you had, and this will lead to very, very different properties. So here I'm just computing the energy density and pressure. But the key finding that we found is that the gravitational potential psi for vector is going to have a 1 over v squared enhancement. So this is equal to psi of vector is going to be equal to 10 to the 6th of the psi of scalar, meaning that we can expect to improve sensitivity by 10 to the 6th. And we can even use this result to get better constraint for pulsar timing arrays, because the gravitational redshift will also change, as well as for astrometry. Another point that's really important is that for vector dark matter, the tensor perturbation becomes significant because of this additional direction u hat. So you're going to have some u hat direction and some k hat direction, which will lead to denser modes that are comparable to the scalar perturbations. Okay, so just conclusions. So we propose astrometry to detect dark matter. That could be used to probe masses as low as 10 to the minus 33 eV. So that's what I showed in the sensitivity plots. Then astrometry complements cosmological probes of ultralight dark matter, which use a combination of CMB and large-scale structure data. And then it could be also used to probe models of quintessence. The key point now is that I think with astrometry we should have seen something related to quintessence that we have not. And then for ultralight vector dark matter, these detection prospects improve significantly by a factor of 10 to the 6. And there's more to come too soon. We're now finishing papers on pulsar timing arrays of ultralight vector dark matter and astrometry of ultralight vector dark matter as well. Thank you.
Any more questions for Sarunas?
Yes.
So I want to understand a little bit better how the actual limits, or like your Gaia limits, would come, because like for the Gaia sample, right, the quasars, while the lead author is a very reliable person, the senior author on that paper is a known crackpot.
Okay.
And I think we can say that, right, reliably? No, I'm just kidding. But seriously, like, so if there's contamination, like these data sets were not necessarily designed to. The samples were not necessarily designed with this in mind. So if there's things that are not quasars in there, what does that do to your limits?
Oh, so here, so for my limits that I showed, again, we tried to be as conservative as possible. So we tried to only take the quasar. We didn't take all 1 billion samples.
No, I know, but within Gaia, right, they have to say that thing there, that's a quasar, and they have to say that with some amount of confidence. Now you can tell me how confident you should be about that. But right, there's some level of confidence. It's not 100%, and there's going to be things which are not quasars in there.
So what do you think, what could be, how large the error could be? Okay, so here for a Gaia data release 5, I expect 2 times 10 to the 6 quasars. Okay, this is, you're saying that maybe it's a little bit optimistic. So what?
No, I'm saying, so how many of your quasars do you think are not?
Yeah, we spend a lot of words on that in the paper and don't come up with an answer.
But it's not one,
But
right?
wouldn't
No,
that
it's
probably
certainly-
to produce apparent signal or noise and not to take it away?
Yeah,
that's
that's
a
why I'm
good
kind of
question,
want to understand, like, is this like,
I'm fan.
Operationally, this appears as an excess noise, right? It's like like chi squared is greater than 1 or whatever after you account for the. So yeah, it is a hard measurement to make because it's fundamentally a variance measurement. So if anything else, whenever something goes wrong with your sample, it always increases your variance, right?
But now if I'm taking 10 to the 6, the number of quasars to be 10 to the 6, so how, is there a way for us to estimate how many clean quasars we have? Like, is it 10 to the 4, 10 to the 5? Like, how many orders of magnitude? Because that will move
even if the sample is clean, there could still be some correlated instrumental noise, right? And so we've done this power spectrum analysis, Neil and I, on the DR2 quasar sample, decomposing it into multiples, and we found at large angular scales there is excess noise beyond this statistical white noise.
In the proper motions?
In the quasar proper motion power spectrum. Yeah. Below L of 20, there's this noise is lower by a factor of 100 in the power compared to the observed.
That's significant.
I mean, it's improving, and I think the R3 has improved, but it's, for large angular scales, this is probably too optimistic at the moment. Maybe they'll fix it over time.
It is a goal to fix it because Gaia needs the quasars to lock down their reference frames, so
Yeah, yeah.
Gaia, you and Gaia are very aligned.
I was actually worrying about sort of the opposite. It just seems like you can think of, I'm not sort of thinking of the right dimensions and so on, but you can certainly think of noise sources that would generate, at some level the noise can always look correlated. So
Yeah,
I'm
yeah.
wondering if maybe Gaia has actually used the assumption that they don't have any correlations to, in other words, would they be making it look like a stronger constraint because they've imposed some, as essentially a calibration? Is that, I'm just so
yeah.
suspicious of this.
Yeah, that's true. So,
But maybe, I mean,
okay,
I
so
dozed off, maybe you showed real data.
yeah, but maybe more like, okay, but we still have NGVLA, which should be more reliable, because even though they have a lower number of sources and they expect roughly 1,000 quasars, but the angular resolution is significantly better. So even though if Gaia gives us some unreliable data, I think NGVLA data should be better. That should be because it's a radio song. So that should be more reliable, and NGVLA constraint would be stronger than Gaia, well, fifth release.
And when you put that VLBI line up there, is that because the VLBI, that's really a line of what should be detectable? That's not not the case that that VLBI has been used to make this measurement.
Yeah,
It's
that's
found
absolutely
with
right. They
0.
need to do their reanalysis.
Yeah,
That's right, exactly,
Oh, I
absolutely.
feel much better. I thought
Yeah.
you were saying you were, and I thought, did I miss that in the talk? I knew I dozed off for a moment.
This is theory.
Yeah.
Still, it's motivating.
Yes.
I'm sorry, I have to ask Calvin's question again. I didn't quite understand your answer. So let's say I look at 10 to the minus 29 EV on the mass, right? I go up to...
Let me go back to just show the bigger plot. That's
yeah.
Oh, sorry. Yeah.
So let me look at 10 to the minus 29 EV, right? I go
10 to the
up.
minus here, right?
Right, so I go up, I basically hit almost local density.
Yeah.
Right, so like in fact, if I go a little larger, the density would be larger than local density. So is your sensitivity like just based on the observation, just based on the observable that you're talking about? Because like, can't I just cut it off at local density in principle?
Yeah, you can, yeah.
I see, okay.
Yeah. No, this is just a kind of design thing, so because we didn't want to cut it off exactly at 0.3, but you're right, you don't really need to include about the 0.3 dB.
But again, on Calvin, what is, rho here is some energy density averaged over de Broglie wavelength center here?
Yeah, that's right.
Average over line of sight to the quasar, right?
Sorry, what was that?
No. Average to the line of sight.
Yes, that's right. But then it's, of course, because the Broglie wavelength is getting larger with the increasing mass, it has to be below local density.
Wait. So those are different things, right? Yeah. Is it the energy density averaged along line of sight of the quasar, or is it the energy density within one de Broglie wavelength of us?
The latter.
Okay.
Yeah.
Because even though you did this sophisticated calculation, it all only depends on the local density. That's what always happens in these calculations.
Well,
right?
it's just like again, we're just this row. We're not like it's not the 0.3 GeV per centimeter cube. It could be something else, because we know it. We know the local density. We know the cosmic density, and with this, we're actually probing it down to the 10 to the minus 11. But I don't think that we don't really know what we can expect. So this is just the whole sensitivity.
But the thing people in the room are confused about is you had this whole line of sight calculation. You had a calculation that had a term at the quasar, a term here, but somehow the parameter here is only about the term here. That's what people in the room are confused about. Because it looks like it's a 2-point calculation, but I think...
No, but the computation, I'm just talking, the computation was done because I'm just talking about the perturbations of dark matter that are everywhere, and they cause the fluctuations at the observer, at the source, and the photon path will change and so on. So this is just the effect of that such ultralight dark matter exists. It would make everything wiggle.
But then your signal is mostly been contributed by the stuff around Earth, so you have a coherent signal. That's I think that's what we're trying to figure out, is that rho should be something measured around Earth.
No, it should be something larger because of the.
I mean, but like it's not because of the stuff around the quasar, but the stuff.
Well, again, yes, we cannot, because the Brillouin wavelength is so large, you cannot use the local density, so.
Right, so just some form of local density.
Yes, that's right. But it's again not the 0.3, it's something else, and this is the parameter part that we're probing.
Can I just ask for the definition of rho again? Like
Sorry, what was that?
what specifically do you mean when you put rho here? Like, is there an expression you have for it, or like what does that symbol mean?
Yeah, so the thing that we do, we know that the energy density is equal to
If you
one
go back
half.
to the equations you actually will fit.
Yeah. But just let me. Sorry, well,
This is making me feel better. I thought I might have missed it.
no, so this is that we know that rho is equal to 1/2 m squared a naught squared. Then we solve for a, and we plug it into the gravitational potential.
But what is the measurement you do?
Because those are both time and location dependent, right? So where are you
Where and
measuring
when,
that rho
yeah.
from?
Wait, sorry, can you repeat?
Right, yeah, so rho is, on average, it's some fraction of cosmic density.
Yes.
But around Earth is some fraction, it's like larger, right? But it's,
Yes, that's right.
you say it's lower, it's still lower than local density, so we want to know that rho, is that rho the average rho across the universe, or is it the rho of this local?
It's the average,
Average over
the whole universe?
I think it's the Broglie wavelength that would be the average.
So is the following interpretation of that plot correct? I pick a mass,
Yeah.
I can compute a de Broglie volume. I
Yes.
go out there, I add up all of the energy inside that volume, I divide by the volume, that's rho.
Yes.
Okay, thank you.
Well, I should continue discussions.
But what
Yeah.
is the measurement? Sorry,
yeah,
now I realize I didn't.
Yeah, we can let people.
We should
Yeah, just in
find out
case
what
people
the
wanna go,
measurement is.
yeah.
So what specifically is, what specifically do you do with the with the Gaia observation?
So. Oh, sorry.
I know, it's good, I'm still trying to figure out March. Okay. So, like, I may not be in the country in March.
That's fine.
If I am, I would love to be there.
Okay, so should we say that?
So the quasars.
Can I just give you a PDF? Yeah, probably.
Oh, I have a backup slide that I could share.
Not
just
a
give me-
file.
I guess it was.
So,
So just let me.
I also have like, I can get shinier screens. So probably I'd say there's like a 3% chance I'll be there.
Okay. Would it be?
So because we're trying to find my speakers, I don't want.
That's fine, you don't have to find it, that's fine, I don't need that, that's fine.
No, what is the measurement? You have a,
Okay.
The angular velocity of some correlated angular velocity of some n sources. So delta theta over observation times the 1/square root of the number of quasars. So
you think that'll be limited by statistics?
Yes.
It seems
How many?
unbelievable it would be limited by
How many
statistics,
quasars are you
right?
talking about? You're
10
talking
to
about
the 6.
But you won't actually be able to correlate
So
10 to
how
the
do you
6.
actually get an absolute measurement of the direction of your, right?
Quasars are usually
To do
done
a
in relatively
correlated-
small regions, it's like complicated. Because the field of view of these things is pretty small.
And he's needing a large scale
So
correlation.
you kind of, but they kind of like, I think the way they work is they kind of like tile them. I mean, it's not, I mean, this is the right starting place for sure. But I think when you start getting into like the sort of technical details, right, you start have to like do these sort of like tilings.
Yeah.
And so the way that could introduce additional noise where you get from here to over here.
And the way you'll calibrate that out is by assuming there is nothing like that.
Yeah.
So you should really read very carefully and really talk to some of the observers how they do that before you make claims so strong about what your sensitivity will be.
Okay.
I mean, it's the right, I mean, it's the right kind of like, I mean, it's a cool idea and it's the right starting point and things like that. But yeah, it will become, once you get into anything, when you get into the weeds on these things, they become messy. But, you know, this is the
pre-mess
analysis, right?
So okay, so just out of curiosity, so if I put all this mess, so how do you think, like, how strong, like, how much would these constraints, I understand that this is very naive, but if I'm being maximally pessimistic, for example, just as pessimistic as possible, like, how much do you think these constraints should look like?
Yeah, I don't know. I really don't know. Because, you know, they have, so, right, because the way these like the LBI and everything work, right, is that you have like these correlated radio signals, and then they assume they have you know, a point source, and then they reconstruct the location of the point source by correlating all these different signals, and then they give you that. And so there's a lot of sort of data processing that goes into just like creating these maps to begin with. So I don't know. I'm not an observer. I've spent a little bit of time trying to think about similar questions, but
No, because that's something that we definitely need to address, like how.
In some sense, the Gaia limits are more concrete because they do at least officially tell you that they think that they have a global reference frame, and that you should believe it within that global reference frame. Whereas I don't think that the ELBI people will write down telling you, here's our global map of all the quasars with their global astrometry over time and how you should think about it. So you, in some sense, I think your Gaia stuff right now is probably more, except for the fact that we were talking about before, where I just don't know how many of those. I mean, you'll have real noise in there because there'll be things which are not quasars in there. Because Hogg actually built this catalog of quasars with a number of people, and it's always a question about how pure you want your quasar sample to be.
But it would still be, I guess, possible to find some sort of like a fraction of how, like, if I have a total sample of quasars, what's the fraction, like, clean?
But I think they're saying because Gaia used it's a selection of quasars to define their global reference frame. But they're saying that there is some correlated motion even in that reference frame. So then if you take that as the reference frame for like a million quasars like that, there's already some correlated noise in there.
That's right.
I think that it'll be a fun exercise when you put real data into it, and I think you'll find out what the things that you need to worry about are. But I mean, I think that it's a cool idea, and and you should definitely try and do that. But I think it will be a fun process.
I mean, now I'm a little bit worried that, like, if the limits are significantly weaker, and I'm like, okay, so again, I'm taking the most pessimistic scenario, they're really
well, I mean, then it just would be, but then it changes, it becomes a different question, right? Then it becomes a question about like, okay, what do you need to do with the real data to get closer to this,
that's right,
this limit, and then so there'll be a set of problems you'll have to solve to do that. So, but probably just like a naive application of the data, there is going to be much worse than this. But then, what you need to do to make it better limit.
Sure. No, but the back reaction.
In your background, or you had some equation where you were summing the three different sources.
the kinematic corrections, right?
Yeah. If I had a stochastic gravitational wave background, you first started out with use astrometry to detect gravitational wave background, stochastic one.
Yeah.
So when does that start overpowering, or can you distinguish between your signal and a sufficiently strong stochastic gravitational wave background?
Well, I think you're just talking about pulsar jamming, gravitational wave, pulsar jamming arrays, right?
Well, yeah, but
Because
astrometry.
I think for astrometry it would be difficult to probe it this way.
Well, you had an example where you put in, you said, I think 1 million stars for Gaia, and you got omega gravity wave 10⁻⁶, but if you put in 1 billion, as you said, for the potential,
Yeah, but that's.
you would get closer to what nano
Oh, yeah.
is detecting. So, it seems like at already 1 billion stars, you're getting close to what there should be some signal there, right?
Yes, but I think that, oh, sorry.
Increases below LF20.
I see.
Is increasing power.
Okay, good, that's very relevant to what we're doing. Because we're working on the spatial distribution, the.
So yeah, that was, so again, this was something proposed by Booking Flanagan in their
Right.
paper, and they estimated this is their upper
And
limit.
the radiance
So
and
of course,
sensitivity variations could
again, this
be
is
related to that,
the
so.
clean sample of
I
lasers
think
that we were
this is
talking, so of
no-
course, if you keep increasing the number of
But it is
quasars,
correlating motion
or the observations, then you're gonna get a better sensitivity.
Oh, sorry, okay, fine.
So that there's 1/n for the upper limit of the gravitational wave energy density. So,
No,
but again, it depends how many clean samples you really have, so
To look
again,
at the spherical harmonics.
the number is supposed to be larger, but
That's exactly what
Wait, would that have any quasars? Not be stars?
Exactly.
no, I
for
think it
sufficiently.
I think for this application, I think it has to be quasars because you need some extragalactic sources, so something very far away. The quasars are just I guess best example that you can use, but probably I'm not sure if you can use stars. I think usually people use quasars.
It relates to a super question I have about Gaia, which I'll ask you next time.
Okay.
Unbelievably.
Let's chat.